Hey, welcome back, chemistry students. I'm Mr. Silverstein, and it's time for you to work on transmutations. So get out your spiral notebook. I'm going to share my screen and let's get started. So we've been working on nuclear chemistry, and today we're going to work on Unit 4, Concept 4, Transmutation of Elements. And so with the big idea, there are 118 known elements. And nuclear transmutation is the conversion of one chemical element or an isotope into another. And because any element or isotope is defined by its number of protons and neutrons in its atoms, nuclear transmutation occurs in any process where that number is changed. So if the number of protons changes or if the number of neutrons changes, you can have a change. And so our objective today is to identify and explain two ways in which transmutations can occur. So you're going to take some notes. There's going to be a little bit of reading. There's going to be a little bit of video. There'll be some calculating and a recap. Quick reminder of the 7 tips for effective studying. Spiral notebook for your notes, pens and highlighters, periodic table of elements. Watch the video lesson, pause as needed, go back and review the slides in present mode to refine notes. Email me if you have any questions. Complete the assignment on the next tab. And remember, only submit completed work. Let's go back to our previous concept and review some things. Nuclear stability is a concept that helps to identify the stability of an isotope. To identify the stability of an isotope, it is needed to find the ratio of neutrons to protons. And in radioactivity, the time interval required for 1/2 of the atomic nuclei of a radioactive sample to decay is called half-life, and that changed spontaneously into another nuclear species by emitting particles and energy. And how long it takes for a radioactive material or radioisotope to decrease by 1/2. And so we call that a half-life. So let's get into the transmutations. Let's first watch this video on the types of nuclear reactions and the types of nuclear decay. And this should take a couple of minutes. You can pause along the way if you want to, but we're going to run this together on this screen.
In chemistry, we're typically interested in the electrons in a compound because it's the electrons which are holding the atoms together in bonds. And chemical reactions involve breaking bonds and making new bonds. But we always have the same number and types of atoms. They're simply rearranging. That's not true in nuclear chemistry. In nuclear reactions, we're actually changing the nucleus of the atoms. And because the type of atom, whether it's helium or xenon or carbon, depends on the number of protons, if we change that number, then we change the kind of atom. And in nuclear chemistry, that's exactly what happens. We have different types of nuclear reactions. We have reactions which involve nuclei splitting up and one atom forming multiple atoms. Those are called fission reactions. We also have fusion reactions, where multiple nuclei come together and make a single atom. And then we also have just nuclear decay process, where one atom spontaneously converts into a different type of atom by spitting out a small subatomic particle. All of these changes involve massive changes in energy. Energy changes which are tens or hundreds of thousands of times larger than in a typical chemical reaction. Because these energy changes are so big, we actually get a measurable change in the mass between the products and the reactant reaction. And that's because mass and energy are related by the theory of relativity. And so nuclear reactions don't conserve mass. where we typically say chemical reactions. And this is a big difference between traditional chemistry, where the atoms are always conserved, and nuclear chemistry, where the atoms change their type.
So I want to take you back in time and talk about a concept known as alchemy. And it was a science that was used in the Middle Ages with the goal of changing ordinary metals into gold. And so the alchemist would attempt to change ordinary metals into gold. Now, we know that can't actually happen, but there was a time where they thought it could. And so the modern practice of chemistry started in medieval Europe and in the Middle East. And alchemists in the 16th century believed that by doing certain chemical reactions, you could turn cheap metals into gold. Now we know that no chemical reaction can achieve this goal. Alchemy is considered magic. And we all know that magic is typically something that is a diversion or a distraction of the reality. However, through transmutations, modern chemists can change one element into another. And that's what we're going to look at today is transmutation reactions. And so transmutation is the conversion of an atom of one element to an atom of another element. And it can occur in two ways, and make sure you jot this down. The first way is through radioactive decay, where the element gives up a proton or a neutron, or it leaves off a beta particle, and you have radioactive decay. The second way is when the nucleus of an atom is bombarded with certain types of particles, a proton particle or an alpha particle. Bombarded means that they crash into each other. We're going to look at that. So many transmutations occur naturally in nature. For example, carbon-14 is made from nitrogen-14 in the upper atmosphere of the Earth. And so it starts out with nitrogen-14, and it picks up one neutron, and it becomes carbon-14. Many other transmutations are done in the laboratory. For example, the first artificial transmutation was done by Rutherford in 1919. This eventually led to the discovery of the proton. And here, he took nitrogen-14 and a helium particle and created fluorine. Now, writing transmutation reactions, and we show this to you just so you can get an idea of what it looks like. The transmutation reactions are written using the following guidelines. First, make sure the sum of the mass numbers are in the top left is the same on both sides of the equation. And make sure the sum of the atomic numbers, bottom left, is the same on both sides of the equation. Let's look at this. Make sure you're familiar with the following particles and their notations, and you should draw a little chart for this. For the alpha particle, it will have a symbol of helium-4, which is element number 2 and a mass of 4. You can also show it as an alpha particle, an italicized A with a 2,4. Beta particle is no mass, but an electron. And that's going to be a negative charge. You can also show it as an E or with an italicized B. A gamma particle is the lambda. The neutron particle is a neutron, 0 protons, 1 neutron. A proton particle would be a helium, mass of 1, a hydrogen, mass of 1, and a proton of 1, or 1,1p, or the positron, which is a positive electron. So jot down that chart so you have it. You can pause the video to get that chart in your notes. All right, so when you write transmutation reactions, you want to identify the missing information. So we're going to do an example here and identify the missing information. So this is what a transmutation reaction looks like. It starts out as one element on the left, becomes another element on the right. Let's fill in some pieces of information. So if we look at the left, we have plurium, and plurium has 94 protons and a mass of 239. If we look at the right, we have an element showing 96 protons and a mass of 242 plus 1 neutron. So the question is, what radioactive element joins plurium to make the transmutation? So let's do the math. If we take purium and we add helium, 94 plus 2 gives us 96. 239 plus 4 gives you 243, but we end up removing 1 neutron to make 242. And so this becomes curium. So plurium takes on an alpha particle and becomes curium. Now let's identify the missing information on this one. Here we start off on the left with uranium. Uranium has 92 protons and a mass of 238. Looks like it's going to join with carbon here, but we don't know which isotope of carbon yet. It results in californium plus 4 beta particles. That big 4 in front of this beta particle says that I've got 4 of them. So if we look at the right, it shows 98 protons and a mass of 246. But we're going to subtract 4 neutrons. Remember, on that beta particle, when you multiply a negative number to a positive number, your answer is always going to be negative. So let's see what happens here. We end up adding carbon 12. So I have 92 protons with uranium, 6 protons with carbon gives me 98. I take 238 mass plus 12 is 238, and that's going to be 250. 250 minus 4 gives us 246. And so the isotope of carbon that's needed to make this transmutation is carbon 12. Now let's do another example. We're going to look to write the beta decay for carbon-14. So we have carbon-14, and we do a beta decay, which removes, multiplies, it adds one electron, one proton, so you end up with nitrogen-14. Let's look at that again. Got a beta particle, becomes nitrogen-14. What about radon? What's the alpha decay for radon? Well, we take radon, which has 86 protons and a mass of 222. We put in our alpha particle, and it's going to subtract that, and you end up with polonium. So let's look at these other transuranium elements. Elements in the periodic table with atomic numbers above 92 are called transuranium elements. Transuranium. So all of the elements with atomic numbers above 92 are called transuranium elements. All of these elements undergo transmutation. They do not occur naturally in nature and are synthesized in the laboratory. These can only occur in the lab. And to synthesize these elements, particle accelerators bombard the nuclei with fast-moving particles. Let's take a look. A particle accelerator, also known as a particle collider or a super collider, is a machine that uses electromagnetic fields to propel charged particles to very high speeds and energies and to contain them in very well-defined beams. These large accelerators are used for the basic research in particle physics. Let's take a look at the Large Hadron Collider. This is a big super collider. It's actually pretty interesting to watch. I'm going to get past the advertisement first.
The Large Hadron Collider. It's a massive, beautiful piece of human ingenuity, engineering, and wait a minute, that's not the LHC. This is the LHC. This is the Large Hadron Collider, or LHC for short. It's a 27-kilometer particle accelerator sitting under the border of France and Switzerland. It's an atom smasher, the biggest in the world, designed and built by thousands of engineers, scientists, and mathematicians from across our tiny planet with the goal of helping other scientists learn about things of incredibly small size by smashing them together. These smashings are called collisions.
This is really all they're interested in. Yeah. They're interested in collisions, collisions, collisions.
That's Mike Lamont. He's the operations group leader working on the LHC. It's his job to run beam. Beam being nerdy lingo for bunches of hydrogen protons that fill up the LHC. The LHC is a ring containing two beams going in opposite directions. But if we look closer, that beam is actually made up of bunches of protons.
In fact, each bunch has about 100 billion protons each. And these bunches are about 30 centimeters long, typically about a millimeter dimensions as they're going around the ring. And so think about a long, thin, tapered piece of spaghetti.
Incredibly powerful superconducting magnets keep the beams flying at nearly the speed of light with the aim of making these proton bunches hit.
Pass these thin hairs through each other, get about 30 collisions. So most of the protons just miss each other and they carry on around the ring. They come back one turn later and they can do it again.
And the reason why they miss each other is because atoms are mostly empty space. So getting them to collide is incredibly difficult. It would be like standing 10 kilometers apart and trying to shoot two needle-thin arrows at each other so they hit halfway. So the key is to do this a lot.
target this year, just to put it in context, is about 800 million collisions a second. So we really have to work hard to get that rate.
Hundreds of millions per second is insane. Imagine trying to control a proton traveling at nearly the speed of light. To keep the bunches on track, the LHC uses dipole magnets, or two magnets. But when they need to steer the protons, they use quadrupole magnets, or four, one on each compass point, applying 300 to 400 metric tons of force per meter.
So we take our pieces of spaghetti and focus them down with very strong quadrupole magnets, like lenses. We get them down to the diameter of a human hair as we pass them through each other in the center of the experiments.
And that is why the LHC is in the business of collisions. The LHC is sort of like your power company, but instead of providing electricity, they're generating collisions. More collisions, more better. They spend all their effort to try and get these bunches of hydrogen ions to hit inside of other scientists' experiments. Of course, having a collision is great, but if a proton collides in the woods and no one's there, does it make a boson? Who knows? The scientists still have to be watching at just the right fraction of a second to discover a new particle. That's where these experiments come in. They sit on the LHC ring at collision points, and they're probably what you think of when you hear Large Hadron Collider. The famous ones are ATLAS and CMS, which spotted the famous Higgs boson back in 2013.
It's called CMS, compact neon solenoid. However, it really is not compact. It's a relative term. As you can see, nothing of that size is compact.
Dr. Talika Bose sits in the control room of the CMS waiting for an exciting collision to happen inside her 3-story science experiment, all thanks to the LHC.
So they collide about 25 nanoseconds. So you have a bunch colliding with another bunch. You may have a proton here and a proton here, which has a hard, what we call scattering, a hard event. And out of that comes out a whole mess of particles.
This is what she's talking about. When two protons collide, it looks like this. To you and me, this may look like a whole mess of particle parts, but to Dr. Bose, this mess can actually tell you what's inside a proton.
There are two important pieces of information that we get from this. One is whether it's curving this way or if it's curving that way. That tells us whether it's positively charged or negatively charged, and then how large is the radius of curvature, because it could be curving like this, or it could be curving in a much larger radius. And this has a direct relationship with essentially what the velocity and consequently what the momentum of the particle is.
And this is why the LHC is awesome. Dr. Bose is basically watching millions of proton car crashes in order to reverse engineer the automobile. Smashing atoms together can reveal what they're made of, but instead of injectors, plastic, steel, and glass, physicists find neutrons, kaons, pions, muons, and neutrinos. By the way, physicists call particles that are made of these things hadrons, hence the name Large Hadron Collider. Proton collisions like these help physicists reveal exactly what these tiny structures that make up our universe are made of. The technology is super advanced, but the science is the same as it's always been. We simply break things apart, hoping to understand how they tick. Before we went to the Large Hadron Collider in Geneva, we were on top of planet Earth, 800 miles from the North Pole at the Svalbard Global Seed Vault. To find out what awesome science we were doing there, check out this video.
You know, this is quite simply a hole in the mountain.
So that super collider is actually pretty neat. You can go back and watch that anytime you like. So let's review transmutations. And remember, we're not having you do a lot of these kinds of formulas or equations. We're just looking at the concept of this transmutation. And a transmutation is the conversion of an atom of one element to an atom of another element. And it can occur two ways: radioactive decay with alpha or beta particles, or when the nucleus of an atom is bombarded with certain types of particles, proton, alpha, etc., in a super collider. Now, there are some questions for you on the transmutation recap. Open up the assignment tab, click into quizzes, and respond to those questions, and you'll have 3 opportunities to do that. Well, that's all we have for you today on transmutations and atomic decay. Remember, these notes And these slides are posted for you on Google Classroom. If you have any questions, email me and we'll get back to you. You guys have a great day.